welcome to a very special edition of Chemistry 111, the all virtual version. So we'll go ahead and get started. Well, we're going to finish Chapter 2 and look at some of the homework. That's going to be what we'll be doing in class. So let's start looking at it. We just finished talking about how to calculate, well, how to figure out the elemental symbol and the proton, electron, and neutron count of the atoms, just based on looking at their symbol, the atomic number, and the atomic mass. And we're weighing individual atoms. The mass is typically too small for us to deal with on an individual. So what we do is we've introduced a new unit called the atomic mass unit, or AMU. I'm going to hop back a few slides, but we use this when we look at individual atoms, if it'll let me. Back. That we look at it, a proton, as I said, weighs approximately 1.0073 AMU. A neutron weighs 1.0087 AMU, and the electron weighs this small little fraction of AMU. Rather than weigh these atoms in grams, which is incredibly small and impractical, we've introduced the AMU that helps us deal individual atoms. Now, an AMU, we get this, we use our standard measurement is we take the main isotope of carbon, the carbon that's in all of our bodies, and set that to be exactly 12 AMU. It's the empirical standard which we base the AMU measurement on. Just like there was maybe originally someone's foot or someone's hand that we base some of the English units on. But so we set carbon 12 being exactly 12 AMU and measure everything according to that. And we measure all the atoms by calculating the total mass of protons, neutrons, and electrons. However, when we're dealing with a large number of atoms, we're going to get some mixture of isotopes. No matter how hard we try, we're not going to get perfect ratio of all carbon 12, all chlorine 35, or all boron 10. And so we have to consider the isotopic abundance, and that's where we get something called a relative atomic weight. So if you look at a periodic table, as we will in a few minutes, you'll notice you have the atomic number up top, and below the element you have a atomic weight. This atomic weight is actually the weighted average of the isotopes. So instead of for carbon, instead of being 12, which is how we set AMU, it's 12.01, meaning 1,000 atoms, you can take 12.01 and that factor in all the carbon 13s and carbon 14s, you'll get chlorine. Instead of being like 35, it's 35.4 for a minute, but that is taking into account the chlorine 35 and chlorine 37. So this atomic weight is the average of isotopes based on how many there are. So, as I said, chlorine has two stable forms, chlorine 35, chlorine 37. With the first one, 35, is 75% abundance. Chlorine 37 is 25. If I picked out one atom in a big pile there's only a 25% chance I'll get chlorine 37. So you'll have somewhere between 35 and 37. In fact, it's a quarter of the way between 35 and 37. Half of the way would be 36. A quarter of the way would have been 35 and a half. And that's why we see typically 35.45 as the atomic weight. Because bromine has 79 and 81, with a relative abundance about 50-50. Technically, it's 51-49, but it's pretty close. So you're half as likely to get a 79 as you are to get an 81. So when they average it, it's closer to 80. Closer to 80. It's about halfway between. So how do they actually calculate that number? So they're going to take the atomic mass of bromine 79, which is 78.91833371, abundance, which is 50.69. I rounded to 51 for the sake, but 50.69. You multiply those two together. You turn this into a decimal. So how do you turn a percent into a decimal? You divide by 100. That gives you, that part. And then you take 80.916296, which is the 81, and multiply its percent abundance. And you add them together. When you add them together, you get the atomic weight. Because we'll rarely, if ever, deal with just one atom. We always want billions and trillions of atoms because we can really work with that much. Just looking at water, if I wanted to do 18 mils of water, which is a small little glass, that is, in 18 mils of water, that's 602 sextillion atoms. So if you took a million, then a billion, and a trillion, and a quadrillion, and a pentillion, then you got sextillion after that. So that is 602 times 10 to the 21st. That should give you an idea how, which is not a whole lot, deals with that many atoms. So this atomic weight is really kind of important when we're dealing with this. Now, there's a few problems on the homework. Maybe one, maybe two. We'll look at those in a little bit. But for the most part, this is not a huge part of this chapter. Now, the last part of this chapter is we're looking at the periodic table. Now, if we were in class, I'd say, hey, look on the wall. Look at that periodic table and look how it looks. It looks funny. It's not like not as boxy and straight and regular as we'd like, but if you know how to read it, it is really amazing when it comes to predicting and understanding the elements. Structure. Excuse me. Size and various other properties at the table. That elements are arranged in the rows, which we call periods, and the columns we call groups. Period has a certain range of sizes that follows a trend for. And this is what we do to the electron count, which we'll discuss in a couple. So they're all like said, like, oh, we have this like orbit of electrons that follow the atom. And as we go across the row, we're just adding electrons to that orbit. And that's going to control a lot of the properties of this. Then as we have groups, change groups based on reactivity. Like lithium will react similar to sodium, which will act similar to potassium, rubidium, and cesium, which are all right over top of each other in the periodic table. They all have one valence electron. They all will react with water to form hydrogen gas and space and produce a lot of heat in the process. So much so that cesium will explode rather violently. All right. Come on. Okay. So where did this periodic table come from? Well, this periodic table came from just gradual discovery of elements. They're not discovered all at once, but in bursts. There's many of them, especially some of them with old names we've known since like the Greek philosopher time. They knew about lead, they knew about gold and iron and some of the other guys. But some of the newer guys weren't really known. In fact, by 1865, just about half of the known elements have been discovered. But with just half that table, two different chemists separately created a version of the table that's very similar to what we see today. Dmitry Mendeleev in Russia and Lothar Meyer in Germany. And so if you look at the table seems pretty straightforward right now, where if you're going from left to right, top to bottom, numbers are always increasing by 1. You have 1 on hydrogen, 2 on helium, 3 on lithium, 4 on beryllium. Then jumping to boron being 5, carbon being 6, 7 for nitrogen, 8 for oxygen, 9 for fluorine, and so on. But this was put together prior to the atomic numbers. Now, they could do this because they knew something about the atomic weights, how they reacted and how heavy they are. But even then, not all of that works, because some of the transition metals, the atomic weights, don't always follow an obvious linear pattern. So they were able to put this in because they could say, oh, this reacts similar to that. Copper needs to go above silver, above gold, because they all react similarly. There's a reason why we've used copper and silver and gold as precious metals for time immemorial, because of how they react. They're really good for coinage metals. And the beauty of this is that they left a lot of blanks in the table for elements that weren't yet discovered yet. That you could figure out, oh, there's an element that goes below silicon that we haven't quite found yet. And I'm going to leave a blank here because I know that arsenic doesn't react like this. So there has to be something that's going to go at, I think Dmitry Mendeleev, cocky bastard that he was, even predicted the atomic weight of some of them. And when the element, I think, was it gallium was discovered, no, germanium was discovered, the guy reported the incorrect weight, and he told him to go back and check his numbers. And the guy did, and tried to, Mendeleev was correct. And so that kind of like cemented Mendeleev's place in history, where he knew more than the scientists who discovered it what it should weigh. But so let's look at this table. We can split it into metals and non-metals. The metals are the whole lefternmost half of this table, where we can split it into different groups of metals. The first 2 columns are the alkali and alkaline earth metals, so named because their willingness to make alkali bases in the presence of oxygen and water. We have the transition metals that gets us from the alkaline into the non-metal region. We won't focus there so much. We definitely won't focus so much about the inner transition metals, which is our radioactive things like uranium and plutonium. We might talk about them briefly next semester when we talk about nuclear chemistry. We have the non-metals. Some of these names we won't really worry about, like chocolagens, don't really worry about, but halogens is a pretty common name that we'll use. Like fluorine, chlorine, bromine, iodine. The noble gas is also a pretty common name we'll use. So named because these noble gases tend not to react. And between the metals and the non-metals are the liquids. Finish this. So quick properties of these guys. So they're a luster or shininess, high conductivity of electricity and heat. So they are able to absorb and transfer heat, which is why we use metal in a lot of our cooking. And all except for mercury, they're solid at room temperature. So mercury is the only. Sure, we can melt iron, but it takes really high temperatures to get there. Now, when we talk about metals in the next chapter, metals are most often positively charged. Now, nonmetals pretty much have the opposite properties. They're non-luster, don't really shine very well. They're often very non-conductive. They're what we call insulators, we can block electricity from flowing. They don't really heat up too easily. There are all sorts of states of matter. Most are gas, there's some liquid, and some solid. Carbon is solid, sulfur is solid, but we have oxygen and nitrogen and fluorine and chlorine and all the noble gases. And these guys, when they're found in compounds, are most often negatively charged. So we have metals that like to be positive and non-metals that like to be negative when we mix them together. And of course, between the two, we have our metalloids, which basically are just properties of both. They have, like, silicon is the best example. It can make bonds similar to carbon, but it conducts electricity as a semiconductor. And so that's why we use it in the circuit boards. It has a lot of the properties we need to put things in place, not have to worry about it melting or like deforming too much, but it can still carry electricity. So that's the end of this chapter right here. Next chapter, we will be looking at the mole, how to turn grams to moles, and a lot about how to name things. How to name the whole heck of a chapter. It's not a whole lot of math, and the really hard math won't really come till later on in the semester. But we have a lot of naming, so we want to. I'll try to teach you some tricks, some ways to memorize, but you may need flashcards. You may need something to help jog your memory to help get these, because we'll be learning how to put nonmetals and nonmetals together, how to put ions and cations and anions together. How do I make them neutral compounds? What are the names of polyatomics? And all sorts of things like that. So it'll be a process. But okay, I want to look at some of the homework, because this homework for chapter 2, lot easier. There's only 13 problems. There's not a whole lot of people enrolled. We still need to get this and get moving. Some of this is coming due this Saturday. I think it's only the first 2 reading assignments and the first 2 learning curves, but they wait for no man or woman. So get on those. Be working on the assessments, even though the assessments aren't due till like the first week of September. There's going to be a whole lot of stuff coming due. It'll be chapter 1, chapter 2 homework. The chapter 3's reading, chapter 3's learning curve, and chapter 3's homework. If you wait to the very end, you're going to have a whole lot of work to do all at the same time, knocking this out. I try not to put a due date on these until then, because it's like, well, you don't really need them absolutely done until like right before the test. But if you wait to the very end, you're stuck with a bunch of cramming, a bunch of cramming. So we're gonna look at this. Okay, let's do a preview. Just gotta let it load. Okay. Okay, so this first one, okay. This first one is not meant to be too hard, but it's meant to make you think. Okay. Yes. Okay. So, oh, zoom in a little bit. Okay. The smallest charge of of electron is negative 1.6 times 10 to the negative 19th coulombs, which is a charge of a single electron. Robert Millikan was able to measure the charge of the small droplets of oil, suspending them in a pair of electrically charged plates. There are possible charges. So if one charge is 1.6, there's a bunch of numbers that aren't 1.6. So what are we expected to do? So the hint says charge because they had extra electrons. Think about the charge in coulombs on a drop that had one extra electron versus one that has 2 or 3. So if you have 1 electron, it's a charge of 1.6. Well, if you had 2 electrons, 1.6 plus 1.6 is going to be 2. If you had 3 electrons, you had another 1.6, you'd have 4.8. Now you keep adding 1.6. 1.6 times 4.8 is not 5. It would be 6.4. No, there's no 6.4. You add another 1.6, you get 7, you get 8. Yeah, add another 1.6, you'd get 9.6. So those are the only answers possible on this one. That would be the answer for this guy. But that's what they're asking you to do. So there's a couple questions like this, asking you to think about the reaction, what we talked about at the beginning of this chapter, just thinking about this and about what was going on and what were they studying, and identify properties of subatomic particles. So which proton, neutron, electron has plus 1? So it's a drag and drop. This one, they're saying using the atomic number, determine the chemical symbol. So we're the atomic number. Remember, the atomic number is protons. So protons tell you what we have. So we don't need to overthink this. Protons will tell us what we have. And if you're like, oh, I don't have a periodic table in front of me, in the hint, there's a link to the periodic table. So you can all symbol. The element, remember, the atomic number is inherent in the symbol. So if you find technetium on the on the table, technetium, on the table, you know the proton count. Because it's neutral, you know the electron count. The thing you have to do then is find how the mass number relates to the neutron count. So that's a not particularly hard question. Some of these, they want you to go backwards. They give you the atomic number and the mass number. Well, they give you the atomic number, the mass number, and they want you to, so what's the element? And then put it up in proper order. So 36, 84. So you'll put the atomic number down there, the mass number up there, and what is the elemental symbol based on the periodic table. So pretty straightforward problem. So how many protons, negative charge, so okay. Oh god. Wait, did I okay. So this one, they give you the mass number. Yeah, so some of these are just like ones. Some of them are giving you a different order. Like the one down here, say ion with the 65, 36 neutrons and a charge of +1. So what is the element first? Identify the elemental symbol, determine the number of protons and electrons. So you'll use the neutrons and the mass number to find the protons. You'll use the protons to find the element. You'll use the charge to find that. So you're just thinking about the periodic table and how to read that. The one I really want to do is look at 9 and 10. So we'll do 9 together, but 10 is very similar. So 9. How do we do this? We're saying, what's the average atomic mass of this? So they give you the mass unit, and they give you the abundance. And so what do you do? Well, the generalized equation is literally isotope 1 times percent as a decimal. And when I say percent as a decimal, I don't mean 75.77. I mean 0.7577. So mass 1 times the percent plus mass 2 times percent plus mass 3 times percent ... for as many isotopes as you have. So I'm going to do this one. Unfortunately, I can't really show you too well. I don't have a board or whatever. So just work it out with me. So I've taken 34.97 multiply by 0.7577. If I do that, I'm going to just write this down in the blank, even though it's wrong. 26.497. Okay, that's that first number. And then I'm going to take 36.97, which is our second isotope, times our percent about 0.2423. And that'd give me 8.958. Now, I'm going to add these two guys together, since those are the two major isotopes. 8.958 plus 26.497 gives me 35.455. So maybe this rounds down, maybe this rounds up, but I'm going to go ahead and write down. It says round to the 2 digits after the second decimal point, so 35.46, 35.45. Either of those should be accepted. But plus an isotopic mass times the percent, so on. So number 10, in this case, I have silicon. So I'm going to take this mass times this percent, four significant figures. So once again, that's probably going to be too small, but a straightforward problem. The only difference is that we have three of them. Now, one thing you should note, which one of these guys is more abundant? Well, the first guy, silicon 28, is 92% abundant. So the mass we should get should be similar to silicon 28. So this should be somewhere between 28 and 29 with a preference of being close to 28. So we can calculate that based on that. And then the last couple problems are ones that involve pairing these up based on the periodic table. So like, oh, identify the elements based on their location in the periodic table, which guys in period 6, group 2, period 4, group 12. So, and then classify these as either, what of these are properties of metals, what are these properties of non-metals. So this, into this chapter should not be too hard. Okay. So, as I said, work on this. Try to get this done in advance. It shouldn't be too hard. Some of these should be rather easy. But if you wait to the last minute, you're gonna have a bad time. But if you need help getting into the course, send me an email. Ask for a Google meeting. I got nothing but free time today. I should be able to help you. If it's outside of my office hours, send me an email. I'll still try to set up some time. I know people have sports, people have work, people have all these things that's going to make your learning life a little more difficult. Work with me, I'll work with you, we'll get this sorted out. Now we have like 15 minutes left. I am going to go ahead and end class early. This is about where I ended for the Tuesday, Thursday course. So takes this time, relax if you need to relax, turn in any lab related stuff that you need to turn in. Just send me, either upload it, images onto Google Classroom, or email it directly to me. Don't really care. Obviously, I'm not going to be in the office until at least Saturday, if not Sunday. So anything you throw under my door, I won't be getting right away. So if you need some help, get some help. If you need help from a tutor, set that up. I know I've trained most of the tutors. I've had them in my class. I've worked them through the motions. They should know how to do all this. Most of them at this point have done this Macmillan. So they shouldn't have too much trouble with some of these problems. They might need some refreshers. But they're smart people. I know. But be working on this. Use this extra time to work on this. Just knock it out. Get it done. As I said, we have the first assignments are due the 22nd, which is tomorrow. I think I said it at midnight or something like that. So if you haven't finished it, get it done. Get it done.